Hi all, welcome to the part 2 video of data handling and artificial neural networks. Outliers and outlier detection. Outliers are data points that is essentially a statistical anomaly, a data point that significantly deviates from other observations in their datasets. Outliers can arise due to measurement errors, natural variations, or rare events, and they can have a disappropriate impact on statistical analysis and machine learning models if you are not appropriately handled. Example, if you have the following data set of the student test score 85, 87, 90, 88, 92, 89, and 45, the score 45 is an outlier. It is much lower than the others because outliers can be valid observation or errors in any data entry, measurement, or processing. Types of outliers. Outliers can be classified into various types based on their characteristics. Global outliers, contextual outliers, and collective outliers. Global outliers, also known as point anomalies, these data points significantly differ from the rest of the datasets. Contextual outliers. These are data points that are considered outliers in a significant context. For example, a high temperature may be normal in summer but an outlier in winter. Collective outliers. A collection of data points that deviate significantly from the rest of the dataset, even if individual point within the collection are not outliers. Outlier detection. Outlier detection is a process of identifying observations or data points that significantly deviate from majority of the data. Outliers can distort statistical analysis, leading to erroneous conclusions and misleading interpretations. When calculating means, medians, or standard deviations, outliers can exert disappropriate influence, skewing the results and undetermining the validity of the analysis. By detecting and appropriately addressing outliers, analysis can mitigate the impact of these anomalies on statistical measures, ensuring that the insights drawn from the data are representative and accurate. Detecting outliers is crucial for enormous reasons. Improved accuracy. Removing or accurately handling outliers enhances the performance and predictability of data models. Fraud detection. Outliers can be symptomatic of fraudulent activity, especially in financial or transaction data. Data quality. Regular outlier detection is crucial to maintain the integrity and quality of data, which in turn affects the decision making process based on this data. Model performance. Outliers can significantly impact the performance of statistical model, machine learning algorithm, and other analytic techniques. By identifying and handling outliers appropriately, we can improve the robustness and accuracy of these methods. Insight generation. Outliers may represent unique or interesting phenomena in the data. Identifying and analyzing outliers can lead to valuable insights such as detecting emerging trends, understanding rare events, or uncovering potential opportunities or threats. Methods for outlier detection. Outlier detection is a crucial task in data analysis, crucial for ensuring the quality and reliability of conclusion drawn from the data. Different techniques are tailored for varying data types and scenarios, ranging from statistical methods for general data sets to specialized algorithm for spatial and temporal data. Some of the techniques are standard deviation method, IQR method, and Z-score method. In standard deviation method, this is based on the assumption that data flows in normal distribution. Data points outside of 3 standard deviation from the mean are considered outliers. It is commonly used to univariate data analysis where the distribution can be assumed to be approximately normal. The steps involved in standard deviation method are: step 1, calculate the average and standard deviation of dataset if applicable. Step 2, define the lower and upper bound of the outliers. Step 3, identify outliers as data points that fall outside these bounds. IQR method, the interquartile range method, focuses on the spread of the middle 50% of the data. It calculates the IQR as the difference between the 75th and 25th percentiles of the data and identify outliers as those points that fall between 1.5 times the IQR below the 25th percentile or above 1.5 times the IQR above the 75 percentile. This method is robust to outliers and does not assume a normal distribution. It is suitable for datasets with skewed or non-normal distributions. Useful for identifying outliers in datasets where the spread of the middle 50% of the data is more relevant than mean and the standard deviation. Z-score method. The Z-score method calculates the number of standard deviations each data point is from the mean. A Z-score threshold is set commonly 3 and any data point with a Z-score exceeding this threshold is considered an outlier. This method assumes a normal distribution and is sensitive to extreme values in small datasets. The steps in calculating the Z-score method is: step 1, calculate the mean. Step 2, compute standard deviation. Step 3, calculate Z-score. Step 4, apply threshold rule. Challenges in outlier detection. Detecting outliers effectively poses several challenges. Determining the threshold, where deciding the correct threshold that accurately separates outliers from normal data is critical and difficult. Distinguishing noise from outliers in datasets with high variability or noise, it can be particularly challenging to differentiate between noise and actual outliers. Balancing sensitivity, an overly aggressive approach to detecting outliers might eliminate valid data in reducing the richness of the data. How to handle outliers in data? Once outliers are detected, in the next step is deciding how to handle them. The approach depends on cause of the outlier, the size of the dataset, and goal of the analysis. Common strategies include removal or trimming, capping or flooring, mean or median imputation. In removal or trimming, the outliers can be removed entirely if they are clearly errors or irrelevant to the analysis. Care must be taken removing too many points may distort the data distribution and reduce the dataset representatives. Best suited for large datasets where a small number of extreme values won't significantly affect overall results. Capping or flooring. Quartile based treatment. Outliers can be replaced with upper and lower bounds. Values above the upper bound are capped at the threshold value, below the lower bound are floored. This method preserves all data points while rescuing the influence of extreme values. Best suited for numeric features with long tailed distribution. Mean or median imputation. Outliers can be replaced with the central measures such as the mean or median of the data. Median imputation is preferred because it is less affected by extreme values compared to the mean. This method keeps the data set size intact with mitigating the impact of outliers. Best suited for datasets where outliers are rare and likely due to errors. Transformation. Transforming data can reduce the impact of extreme value. Common transformation include logarithmic transformation and box cost transformation. Logarithmic transformation were useful when data spans multiple orders of magnitude. In box cost transformation, converts queued data to more normal distribution. This method is useful when preserving all data points is important, but their influence needs moderation. When to drop or keep outliers? Dropping outliers should be done cautiously and only when there is clear evidence that they result from errors rather than real observations. While some outliers arise from data entry or measurement mistakes, others represent meaningful rare events, so their cause must be carefully examined before removal. When you should drop outliers? When the value is clearly incorrect. If domain knowledge confirms that value is impossible, example human age of 200 years, it can safely be removed. When you have a large data set, in large samples, removing a small number of questionable outliers usually does not destroy the overall data distribution. When verification is possible, if you can revisit the data source and confirm that the observation resulted from an error removal is justified. When you should not drop outliers, when results are critical or high risk. In safety critical or scientific application, example, aircraft system failures or medical data, even extreme values may carry crucial information. When many outliers are present, if a large portion of the dataset appears as outliers, it likely indicates an underlying pattern. Data shift or segmentation issues that requires deeper analysis rather than removal. When outliers represent real phenomena. In domains like fraud detection, anomaly detection, or rare event modeling, outliers are often the primary focuses and should be retained. Applications of outliers. Outlier detection plays a crucial role across various domains, enabling the identification of anomalies that can indicate errors, frauds, or novel insights. Here are some of the applications of the outlier detection with specific examples. Financial fraud detection, fraud detection in financial transaction. Example, unusual large overseas purchase using a credit card. Cybersecurity, network intrusion detection, example, sudden spike in data transmission to a new external IP. AIML modeling, data cleaning to prevent model skewing in training data, in reducing bias, detects biased predictions. Anomaly detection in big data and cloud system. Cloud security to detect unauthorized access in large scale cloud environments. Ensures integrity by flagging corrupted entries. Thank you all. The part 3 of the unit 2 will be presented in the next video. Thank you.